Welcome to today's webinar. Today we will show you how you can calculate and design an aluminum carport in RFEM 6. My name is Andreas Hörold. I'm responsible for marketing and public relations in the company Global Software. For instance, German and English webinars, technical content of the website, newsletters, and so on. I will be the moderator today and I will answer your questions during the webinar. My colleague Sonja von Bloh will be the presenter today. She is responsible for the development of the add-on aluminum design and for the program R section. And she works also in the customer support team. You can ask questions when you click at the button with the question mark, then enter your question in that field, press send, and I will receive your question and I will answer you. The other way is to watch the entire webinar and then email your questions to info@global.com. Okay, that's for the moment all from my side. I hand over to Sonja. Sonja, it's your turn.
Thank you for the introductory words. I would also like to extend a warm welcome to today's webinar. This webinar focuses on the modeling and design of an aluminum carport. First, I will model the structure, then I will define the actions with particular emphasis on wind loads for a canopy roof. After that, I will design the carport using the aluminum design according to Eurocode 9. Finally, I will show how the structure can be optimized if the design checks are initially not satisfied so that they are ultimately fulfilled. Let us start with the first step, modeling the carport. First, I create a new model and I define the model name. In the Add-ons tab, I activate the aluminum design add-on. Under Standards 1, I define the relevant standards for loads, the combination wizard, and the design. I select the European standards with the German national annex. In the Settings and Options tab, the checkboxes for member representatives and member set representatives are already activated. A representative is a reference member with identical properties. The representative settings can then be defined in the Member Representatives and Member Set Representatives tabs. RFEM automatically detects similarities between members and groups them. Properties such as effective lengths can then be conveniently assigned via the representative, so they do not need to be defined individually for each member. At the same time, members with identical properties can be easily identified. In the Model Parameters tab, I define the location. To do this, I import the location from the map and choose the company headquarters in Tiefenbach. The load wizards for snow and wind then automatically use the corresponding location values. For the carport, I use an aluminum material that I import from the material library. I use here the search function to find the desired material. The columns are assigned the square hollow section. For this, I create a new cross-section and I import this cross-section from the cross-section library. The cross-section should have the dimension 100, 105. The longitudinal beams use the rectangular hollow section. For this, I create a cross-section and I open the cross-section library again. And then I choose here the 184 cross-section. The transverse beams are defined using also the rectangular hollow section. For this, I create a new cross-section, but because I want to define the dimension of the cross-section, I use here the parametric cross-section with manufacturing type cold formed. Then I have to define the dimension. Height is 80 millimeter, width is 60 millimeter, thickness 4 millimeter, and radius 4.8 millimeter. First, I set the working plane to YZ and activate the view in X direction. I model the columns as beam members using the previously defined cross-section number 1. I place the first member at the coordinate origin with a length of 3 meters. I then copy this member in the Y direction using the move copy function. Here I define the displacement vector about 4.1 meter. Next, I define the transverse beam, also a beam member, but using the cross-section number 3. At the member start and end, I assign hinges. To do this, I activate this checkbox hinges, and then I create a new member hinge type with phi y and phi z hinge, and I assign it also to the member end. And then I can create the member between the two columns. I then copy the entire frame twice at spacing of 3 meters in X direction. And next I create the longitudinal beams as a beam member, but without hinges and with cross-section number 2. After that, I copy the front and middle transverse beam twice at a spacing of 1 meter. I then connect all members using the function connect lines members. The roof plane is to have an inclination of 5 degrees. For this, I use the function chamfer. This allows selected objects to be rotated while only one coordinate direction is adjusted. This ensures that the columns remain vertical when rotating the roof plane. I therefore select all objects in the roof plane, and then I choose the function chamfer. Here I define a rotation angle of 5 degrees about y-axis in direction z relative to the origin. I model the roof covering as a load transfer surface in order to apply the load later. To do this, I create a new surface from type plane with stiffness type load transfer, and for the definition I choose the boundary lines. To ensure that the top edges of the transverse and longitudinal beams are aligned, I define a member eccentricity for the transverse beams. To do this, I select all transverse beams using the member representative and create a new eccentricity. To do this, I activate the option eccentricity and define a new eccentricity type. I use the automatic arrangement based on a reference member. As a reference, I select a longitudinal beam and define the top edges as the reference. I assign the eccentricity to both the member start and member end. The advantage of this automatic arrangement is that I do not need to manually determine the eccentricity. In addition, the model remains flexible. If the geometry or cross-section changes later, the eccentricity is automatically recalculated, ensuring that the top edges remain aligned. After that, I adjust the member rotation of the transverse beams. I also let the program determine this automatically based on the load transfer surface in the XZ plane. For this, I use the rotation type surface, and then I select the load transfer surface and the plane XZ. Finally, I define the fixed supports at all base nodes. To do this, I assign the nodal supports from type fixed to all base nodes. The structure is now complete, so I can define the loads. The load case self-weight is already defined. Here the checkbox active self-weight is already activated so that the self-weight of the structure is taken into account. For the roof covering, I additionally define a surface load, and I do this directly in the load transfer surface. Here I define a surface weight of 0.4 kilonewton per square meter. I can check the load distribution on the members via the context menu, loads from load transfer surfaces. For the design of a canopy roof, such as this carport roof, the load determination is carried out according to section 7.3 of Eurocode 1991 part 1.4. I would also like to briefly explain these wind loads below. On this slide, you can see an excerpt from table 7.6 of Eurocode 1991 part 1.4. I have limited the representation to a roof inclination of 5 degrees, as this corresponds to the example. The focus is on the force coefficient CF. This is used to determine the resulting wind force for the design of the structure. The net pressure coefficient CP-net, also included in the table, is not shown here as it is not required in this example. It describes local pressure and suction effects on individual roof surfaces and is mainly used for the design of components and fixing. The magnitude of these coefficients depends mainly on two influencing factors, the roof inclination and the blockage ratio phi. The blockage ratio phi describes the ratio of the obstructed area to the total cross-sectional area below the roof, considered perpendicular to the wind direction. Two limiting cases can be distinguished. For a completely empty canopy roof, phi is equal 0. This situation is shown in the upper figure. In contrast, a fully blocked roof corresponds to phi equal 1, shown in the two lower figures. The resulting wind force acts differently on the roof depending on the wind direction. The figure shows this for wind approaching the eave side for the opposite wind direction. To generate the wind load, I use the wind load wizard. This helps me to apply wind loads to members of surfaces and in accordance with the standard. Here I select the roof type canopy roofs and here the type flat monopitch. To define the surface load plane, I select the roof corner nodes. The order A, B, C, D according to the graphics scheme is important. The line AB represents the eaves line. So I pick first here the nodes AB and then CD. In the parameters tab, the wind load parameters are defined. Since I already specified the location in the base data, these values are automatically adopted. Additionally, I define the structure height H. In this case, it corresponds to the ridge height. I can either enter it directly or determine it by clicking 2 points in the workspace. But it's here 3 meters, so I define it directly. Since I'm considering a completely empty canopy roof in this example, I set the blockage ratio to 0. I then generate the load cases for the wind loads using the Generate Load Cases button. The corresponding information can be found afterwards in the Results tab. And you can also display here the wind loads in the working window. Now let us move on to the snow load case. To generate the snow load, I use the snow load wizard. This facilitates the standard compliant application of snow loads to the model. I select the type flat monopitch. To define the surface load plane, I again select the roof corner nodes in order A, B, C, D. According to the graphic scheme, the line AB again represents the eaves line. In the Parameters tab, the snow load parameters are defined. Again, since the location has already been defined, the values are automatically adopted. The load wizard also offers additional options, such as considering snow overhang. I generate the load case using the Generate Load Case button. The details of the generated snow load can be found in the Results tab. And you can also display the snow loads in the working window. I perform the stability checks according to Eurocode 9, section 5.2.2, paragraph 3b. In this method, global imperfections are applied and the internal forces are calculated according to second-order theory. The stability checks is then carried out on the equivalent member with the buckling length set equal to the respective member lengths. An important note in this context: member imperfections are already taken into account in the stability checks according to Eurocode 9, section 6.3. However, for frames sensitive to second-order effects, local bow imperfections of members additionally to global sway imperfections should be introduced. Whether a structure is sensitive to second-order effects can be checked automatically by the program. Only if the sensitivity exists are corresponding local bow imperfections considered. In this example, I omit this and do not define additional bow imperfections. In the next step, I define the global imperfections. First, I define the imperfection in the X direction. For this, I create a new imperfection case plus X. In this case, I define a member imperfection from imperfection type initial sway. You can see you have here several imperfection types available, also the initial bow and criterion, what I said before. I use here the definition type relative and define an initial sway of 1/200 related to the global coordinate system in imperfection direction X. Then I have to choose the members where I want to assign these imperfections, and then I click on OK. If you want to see the generated imperfection, then you have to activate here the Show Imperfection button. I then copy this imperfection case and rename it to -X. All previously defined imperfections are automatically adopted, so I only need to change the direction to -XL. I will do this in the corresponding imperfection case. Here I choose global in reverse X. Next, I apply the same procedure to the Y direction. So I copy both imperfection cases and I rename it to +Y and -Y. and then I have to change the imperfection direction to +y, and in the other case to -y. The load combinations are to be created according to Eurocode 1990. That's why I selected the standard in the base data. If I open the load cases and combination, you can see this also in the tab base, that here the standard group 1990 is chosen. Also, the combination wizard is activated for the automatic creation of load combinations. For this, I have to define the options of the combination wizard, and for this I open the combination wizard. Here I choose the second order analysis so that the load combinations are created to second order analysis, and the checkbox consider imperfection cases is already activated so that the imperfection cases are also considered. Then I can create here the load combinations. The structure and actions are now fully defined, so I proceed with the aluminum design settings. The longitudinal beams consists of several individual members. To design them as a whole component, I group them into member sets. For this, I select them via the member representatives, and then I choose here this function create member set. Then two member sets are created, and since I want to design the member sets, I activate in the member sets the design properties. The essential boundary conditions for the aluminum design are defined using representatives. Based on the previously defined criteria, RFEM has identified 5 representatives, 3 for the columns and 1 for the longitudinal beams and 1 for the transverse beams. I begin with the columns and define their design properties. For this, I select here the member representatives and click here on Edit. And then I have to define the design types. In principle, local cross-section reductions for tension checks and transverse welds can also be defined here, but these aspects are not relevant in this example, so I don't define local cross-section reductions or transverse welds. In the first steps, I create a new type for the effective length, and I specify which forms of stability failure are to be considered. According to Eurocode 9, section 6.3.1.4, torsional buckling and lateral torsional buckling can be neglected for hollow sections. Therefore, I deactivate these checks. In the nodal supports and effective length tab, I then define the support conditions. The columns are restrained at both ends in the Y and Z direction. This is already defined here, so I don't have to modify this. The checks are organized in so-called design configurations. If no configuration is assigned to an object, no design is performed for it. In the ultimate limit state configuration, I define the basic settings for the ultimate limit state design, such whether a stability design has to be performed or not. For the columns, I omit the serviceability limit states check and therefore do not assign such a configuration. Next, I define the design properties for the transverse beams. And here again, I define a new type for the effective length, and I deactivate torsional and lateral torsional buckling checks, as these are hollow sections. The transverse beams are restrained in Y and Z direction, similar to the columns, so I don't have to modify this here. For the transverse beams, serviceability limit state checks are also to be performed. Therefore, I assign both an ultimate limit state and a serviceability configuration. In the serviceability configuration, the limits for the deformations are defined. These can be specified relative to the member lengths or as absolute values. Different beam types can also be distinguished, such as simply supported beams or cantilevers. In this example, I use the default settings. The beam type is determined automatically via the design supports. If supports are defined at both ends, the member is considered simply supported. If only one end is supported, it is considered as cantilever. For the transverse beams, I define supports in Y and Z direction at both ends, and for this I create a new support type and I name it Y and Z, and here I activate the supports in Z and in Y direction. You see now if only one design support is assigned to this member, the segment type is set to cantilever, and if I choose here the design support also at the member end, the segment type is a beam. As check directions, I choose the local Z and Y direction. Now I proceed with the longitudinal beams, and for this I choose here the member representatives. And here, once again, I define a type for the effective length. I deactivate torsional and lateral torsional buckling. Since there is a column in the middle of a longitudinal beam, I take this into account by including the intermediate nodes from the member sets. And For this, I activate this checkbox here, and then I choose the member sets. Now the nodes are imported in this dialog. I can also switch between static and dynamic image, so that I can see here that I have to apply my nodal support here in the middle on sequence node number 3. And here I define a support in Z and in Y direction. Serviceability checks are also due to be performed for the longitudinal beams. As design supports, I assign the previously defined support conditions to the member set start, member set end, and to the middle of the member set. All defined types can also be displayed graphically in the workspace. In the navigator display under aluminum design, it's possible to activate the member effective lengths. It would be also possible to show here the design supports if this checkbox is already activated, but if I don't want to see this, I can deactivate this. This facilitates input verifications and provides clear documentation. The remaining settings are made in tabular form. For this, I open the aluminum design. In the design situations table, all situations available in the model are listed. Here I can define whether and how they are considered in the aluminum design. The assignment is initially made automatically based on the selected standard, but can be adjusted if necessary. In this example, I limit the design to the ultimate limit state and quasi-permanent serviceability state, and I deactivate the others. In the Objects to be designed table, all relevant model objects are listed. Using the corresponding column, I can exclude specific objects from the design. All remaining entries are then designed by the add-on. Then I start the calculation. After the calculation, the results are available in structured tables. Additionally, the results can be displayed graphically in the workspace. Detailed design information, including intermediate values and formulas, can also be viewed. I open here the stability design, and there you can see the section classification for examples and the formulas of the design. Further evaluations are also possible, such as result distributions along the cross-section. The aluminum design checks are currently partly exceeded, while other members are only slightly utilized. If the structure is to remain unchanged, meaning no additional members or bracings are added, the cross-sections can be adjusted instead. In the aluminum design add-on, it's possible to define alternative cross-sections specifically for the design. This is an iterative process. Cross-sections are gradually modified and checked until the design requirements are satisfied. For the longitudinal beam, for example, I can define a different cross-section for example, here this cross-section. However, the aluminum design add-on also provides a function that performs this iteration automatically. In the global settings, I can define the target utilization for optimization. By default, this is set to 1. Optimization can be carried out within a profile series or using a so-called favorite list. A favorite list can also include different profile series. Let us look at this in detail. The columns currently have significant reserves. In addition to the existing square hollow sections, I would also like to allow rectangular hollow sections. To do this, I create a favorite list, and for this favorite list, I add square and hollow sections. First, I create the favorite list and I name this square and rectangular. And in this list, I add the square hollow sections 1994, 1995, and 1996. And I also add to this favorite list rectangular hollow sections. For this, I open here the rectangular hollow sections, and here I want to add 140, 83, 140, 84. I can check the cross sections that are included in this favorite list. If I open this here, I see these cross sections are included. And then I can choose here this favorite list for the optimization. The longitudinal beams are defined using standardized profile series. The program can automatically determine the optimal section within this series. The transverse beams here, on the other hand, consist of parametric profiles. For these, I can define which parameters are to be optimized, such as height, age, or width will be. And I want to show you this also. Optimize current row. In this case, I only want to optimize the height, age. To do this, I activate the corresponding parameter and define the limits. The minimum value of 95 millimeter, maximum value of 120 millimeter, and a step of 5 millimeter. The program then generates a list that you can see here of all cross-section variants to be analyzed. I then start the calculation. It is important to note the design checks are carried out for all cross-section variants using the internal forces from the original structural analysis. The effects of change stiffness on the overall system, that is, on internal forces and deformations, are not taken into account. To apply the optimized cross-section to the model, you can use the function to apply these optimized cross-section to the model. I will show you this now. You can see here now all design checks are fulfilled. And to use the optimized or all optimized cross-section in the model, I use here this function. And then I start the calculation again. You see now the internal forces has to be calculated. And then the design check has to be carried out. And you can see here all design checks are fulfilled. This brings us to the end of the webinar. You have seen how an aluminum carport can be modeled, loaded, and designed according to Eurocode 9, including the possibility of targeted cross-section optimization. I will now hand over to Andreas.
Thank you, Sonja, for your presentation. At the end of the webinar, I have additional hints, for example, to our online courses. Whereas the RFEM 6 course, it's a course for beginners. Then the Eurocode 2 course for the reinforced concrete design with RFEM 6. The Eurocode 3 course for the steel design. The Eurocode 5 course for the timber design. The Eurocode 8 course for the earthquake design. And the AI Masterclass course. For more information, just click at the links here or scan the QR codes. You can get the RFEM 6 course or a Eurocode course for free when you submit your customer project and when we publish it. You can click at the link here or scan the QR code. You reach a website form. You can upload your files there. The other way is to write me an email to info@lubal.com and I will write you back what files I need. Then a hint to our free online services, for example, the Lubal community. You can ask questions there and our support team or our users will answer you. Then there's the GeoZone tool for the determination of wind, snow, and earthquake loads. You can determine cross-section properties on our website, download 3D models, for example, as a template for your project. You can download the free trial versions of RFEM 6, RSTAP 9, R-Section, or R-Wind 3. And you can explore our online services when you click at the link or scan the QR code. You can find more information on our website, lubal.com, for example, the recorded webinars, knowledge base articles. You can ask the AI assistant Mia all the time, 24/7. Just try it. Okay, that should be also all from my side. I thank you for your attention. Thanks to Sonja again for your presentation. I wish you all a nice rest of the day. I hope we meet each other in a future webinar. See you then. Bye-bye.